Welcome! In this video we will cover how you ensure your programs run as fast as possible in the PowerBasic Console Compiler. All of these techniques we will show today will work just as well in the PowerBasic Windows compiler too. Today we optimize for speed. So with this video we're not going to be using any of the libraries we've built up in the previous tutorials. We're going to start from scratch. What we want to do in this video is create a reasonably simple function that we can time. So what we have here on screen at the moment is just the skeleton of our program. The main pbmain function, displaying a console, and then finishing. So what we want to do here is we want to set the value that we're going to be passing to the function. Initially to be set to the value 0. And then we're wanting to take a value out from the function. And since we're going to have several different versions of this very simple function, we'll call it funcalc1. We'll pass in the variable which is initially going to contain the value of 0, and we're going to get out of the function an output value. Now we'll want to put that output out to the screen so we can actually see it, just so we can be sure that each time we call these functions we're going to get the same value back. Now, how are we actually going to time how long it takes to perform each of these functions? How could we tell how long it takes? Now, what we've done in previous videos is we've used the timer function. The timer function is very easy to use and it returns quite happily the number of seconds since midnight. Now, that's a reasonable thing for most functions, if a function takes many seconds to run, but some of our functions may be very short in duration and take much less than a second to run. So the timer function won't give us the degree of granularity we're actually after. So we want something a little more precise than just a timer function. PowerBasic does actually provide something out of the box we can actually use, called ticks. Now, if we look up ticks in the help file, you'll find that what ticks actually does is it measures elapsed CPU cycles. You put the ticks command with a quad variable before you want to start your timer, and you use ticks end at the end, and the quad variable ends up with a number of CPU cycles that are the duration between the two ticks commands. This is ideal because there will be a large number of CPU cycles every time you run around any function, so you can quite easily see the difference between them, even if the functions run very, very quickly indeed. So, if we want to ticks, we've created a variable up here called qcount, which is a quad integer, which is going to contain some very large numbers. We can, before we do our output, we can then do a ticks end. Now, that'll give us a number of cycles. So if we want to put this in, we will then add it to a string, put in the variable containing it. Now, since it's going to contain many thousands of values, we want to actually put in something with formatting in it. And we'll say this is CPU cycles. So this first iteration will pass a value of 0 into the calculation and get an output that will end the counter, and it will display the number of iterations and how long it took in CPU cycles. So let's create the actual function now, the one that's actually going to do the work. So this is just going to be a standard function called funcalc. It's going to take in the variable as along, it's going to return along. Now each of these functions is going to perform the same process. So what we're going to do is we're going to set a local variable up, which is going to be our loop counter. We are going to do a for next loop. For 100,000 iterations. And we're going to take the long value, and in this first iteration we're going to make the long value equal to the long value plus 1, and after it's finished that, we will then return the value to the calling program. So this isn't a particularly complex function, but it's easy to actually say it's going to eat some CPU cycles. So if we try compiling this, assuming we've been no errors, we haven't, and if we run this one now, there we go. It has done 100,000 iterations quite happily, and it's performed that in 823,000 cycles. So there's our benchmark. So what we want to look at now is this the most efficient way of actually doing it? Since you've now got a performance measure on how long the function takes to run, you can actually tweak it and say, well, if that takes 800,000, is there a faster way of actually doing this? So we'll clone the function, and we'll look to say, well, rather than just saying long value equals long value plus 1, is there perhaps a faster way of actually doing it? Well, what we'll try is we'll use this construct, long value plus equals 1, which performs functionally the same exercise, but it does it slightly differently under the hood. So does this run faster or slower than our original calculation? Well, if we go up to our original calculation and we copy that call, and rather than calling func1, the only change we're making is calling it number 2. So if we run that now, it's going to run the first calculation first and then the second, and we can see from that how long they take. Well, 823,000 cycles to 842. It would appear the second one is not as efficient. Just in case there was anything running in the background in the machine that actually slowed it down, let's try it again. It has been slightly different. The first one is actually slower than the second one. Because a Windows machine can actually run many things at once, it really depends what's going on in the background. So you may want to run your tests several times just to make sure that you're getting consistent results. So it does seem to vary. They are similar. There's not a huge difference in timing between them. But it does appear that the first one and the second one jockey for position. It could be either. So there's no real gain in actually doing the function this way. So is there a faster way of actually doing it? Well, let's clone it and try another way of doing the same thing. And we'll call this funcalc3. Now rather than doing this, we will use the increment command. Now the increment command, quite basically, if we do a help on that one, adds 1 to the variable. Straightforward increment, nothing particularly complicated. But does it run any faster? So let's clone our code again. And we'll now run number 3 alongside number 1 and 2. Well, that's different. Now that is significantly faster. It's 100,000 faster than, at least more than 100,000 faster than each of them. Let's try running that again. Still faster. So it does appear using the increment command, tiny change to the one function, does give you a significant change in the number of CPU cycles actually used. Now, it's not a huge difference, but it's significant. So this is one way of actually saying, well, which command is the best one to use if you want to optimize your code for speed? Well, in this case, the increment command seems to be a clear winner. So one way we're going to do this to make it slightly faster is there's a specialized type of function called Firstbook. Now, Firstbook can be used to run our code a little bit faster because it doesn't have some of the overheads of normal functions. It does have limitations, and one of the limitations is normally you would pass a variable by reference, basically as a pointer to where the variable exists in memory, but for this one we have to use by val, and in Firstbook. So what we're going to do is exactly the same as we did up here. The only difference being is we have to use static variables rather than locals. Again, this is a limitation of the Firstbooks. But for the rest of it, the code is going to be very, very similar. We're still going to do 100,000 iterations, and at the end we are going to return the long value. So very similar to the function we did above, we're still using the increment, but we're actually calling the function slightly differently. So if we go back up to our code and we clone this piece and make that number 4, and if we try running this, we will see we haven't really gained anything. The number 2 function seems to be eating up the clock cycles. This one is shorter than the initial way of doing it, but it doesn't seem to be much faster than the one before. So let's just try that again. It's much the same, it's not that much faster. If we were doing something much more computationally heavy in our Firstbook, we might see some benefit. Well, we're seeing a little bit benefit now. Again, our times seem to be going down, which is good, so we are getting faster. Maybe slightly, not much. So, is there a way of going much faster? Well, there is one we haven't tried yet. One of the things that PowerBasic does is it does allow you to drop down and actually use inline assembler. This is something you wouldn't normally do for most of your functions, but if you actually have the need for speed, then for some types of application, possibly encryption, you may want to drop down to this. For 99% of your coding, you'll probably never ever need this. However, we're still going to call it as a function. We're still going to pass the value in to our function. However, inside here, we're actually going to be using assembler. Now, PowerBasic by default uses registers for all the long variables just to speed things up. So we're giving it a compiler directive to say don't do that for the moment. We don't want anything into the registers. We can quite happily still set our counter as a long, and we can load up our counter with 100,000 as we've done previously. Inline assembler is always preceded by a exclamation mark. And what we want to do is we want to move into the ESI register the variable contents that are in long R. And this is going to be us setting the loop counter. And just to be sure that our value we're going to be incrementing is 0, we can actually do this, which basically subtracts the EDI register from itself which effectively makes it 0. The other thing we're going to do is we're going to make sure that our code is aligned on a power of 2 boundary, which ensures the code runs as fast as possible. One of the things that PowerBasic does actually, it does a lot of low-level stuff if you want to actually do stuff in assembler. Normally you wouldn't need this, but it does. We are trying to get something as fast as humanly possible in our code. So we will set a label which we're going to loop around, and what we want to do here is we want to add 1 to the EDI register, which is going to be our variable which we're incrementing. So I'll be add 1 to the counter. These are just comments I'm putting in. Then we want to decrement, take 1 away from the ESI register, which is our loop counter. Now, having done that, we want to test to see whether the value in the ESI register is actually reached 0 or not. Have we done 100,000 iterations? So we do a jump if non-zero. So if it's still above 0, then we want to go back to our label, which we created a moment ago, label 1. Loop if non-zero. And if we get to the next line of code, the value in ESI must be 0 because we've got here, otherwise we would have looped. And then what we want to do, we want to use the move command to move a value basically to the return of the function for whatever's in the EDI register. And that's it. Then we just end our function. Now, so what this does is it takes in the value initially of 0, it sets up a loop counter of 100,000, it copies that into one of the registers and makes sure that the counter we're going to be using is 0. It then adds 1 to the counter, decrements the loop counter, jumps back up to the label if it's non-zero, runs around that loop until it is 0, and then returns the value of the EDI to the function, which goes back to our calling program. So if we copy the code we had up here, and we're calling number 5, so we try running that now, we're going to basically be running 5 different functions, each of them returning a number of CPU cycles. So if we run that now, what have I done? Oh, I've miscalled my label. Small typo. Run that one now, and there we go. Now you will see from this that each of the 5 functions is returning the same number of counts, 100,000. So each of them has done the same job. The final one running assembler is actually running considerably faster than all the rest, as you'd expect since you've actually hand-coded it in assembler. Now looking at everything else, the fastest one at the moment is number 3. So if we have a look to see what number 3 actually does, number 3 is the straightforward increment. So for using normal basic commands, it would appear that using an increment of a variable is the fastest way to add 1 to it. So if we run it once more, just to test it out, well, it's not much difference between number 3 and number 4 by the looks of it, but number 5, the assembler approach, is significantly faster than everything else. So if we were doing something that really needed speed, and it was something that was easy to do in assembler, then that's how it would be the best place to do it. But these techniques we've used using the ticks command to measure the number of CPU cycles that have been executed between 2 points gives you a nice easy way of saying, well, is anything I've done to this function going to make it slower or faster? And if you want your code to run as fast as possible, you need tools like this to actually measure it. Of course, naturally, you wouldn't use the tix command in a production application. This is purely for you as a developer to ensure your code runs as fast as possible. So, that completes our timer testing code for today. Thank you for watching.